Okay. Okay, recording is started. Now, what I plan to do is, after I cover what I need to today, hopefully it will not take the entire time, and then we can talk about certain homework problems, especially 3.2.20, which is kind of a bear. Yep. Regardless of what time I have in class, I have included some hints in the notes. Hopefully I'll have time to talk about the hints during class, but and I know I'm undermining this with my late start. Sorry about that. So at least I'll have those, but hopefully I can talk about them too. Okay, screen share time. Okay. Dang it, the text is too small here. Okay. So what we arrived at, where we left off last time, was that solving a full rank least squares problem. So we're trying to minimize norm of b minus ax, and there are two ways to do that. One was set up the normal equations and solve them, but those are terribly conditioned. The other way is to compute the QR factorization, and that's what we're going to focus on all this week and into next week. So for now, we're not going to set aside the least squares problem, because once we have a QR factorization, I already went over how you actually use it to solve the least squares problem. Here, we're just going to focus on the factorization. So A is some rectangular matrix, so possibly more rows and columns. QR factorization has an orthogonal matrix Q that is M by M. So this is going to be rather large square matrix. R has the same size as A and is upper triangular. So I'm going to spend the next 3 class periods talking about 3 different approaches to computing its factorization. This is one per class. So today's topic, Givens rotations, also known as Jacobi rotations. The striking thing is these rotations were actually invented by Jacobi, but he uses them for a different problem. So in this setting, I guess it's Givens who made use of them, so we're named after Givens. Go figure. Okay, so that's today, and then on Wednesday, householder reflections or household transformations is another approach to computing QR factorization, and then one that you may have actually seen in a linear algebra class, like a regular linear algebra class, not numerical, called Gram-Schmidt orthogonalization. It may not have been associated by name with a QR factorization, but effectively that's what you were doing. It's actually the worst method of all 3, and that's how it goes with pure math classes compared to numerical analysis classes. Pure math classes will show you probably the intuitively simplest and least practical and effective method for solving all kinds of problems. And then numerical analysis classes clean it up and find better methods. Okay. What is exactly a Givens rotation? It's somewhat similar to the kind of row operation that you're now familiar with for Gaussian elimination, but you have to keep in mind orthogonality, and that's why Gaussian elimination style row operations by themselves are not helpful to us. So in Gaussian elimination, you are starting from matrix A, you're swapping rows, and then you're performing row operations to reduce A to this upper triangular form U. So we want to do the same kind of thing in that we're reducing to upper triangular form, but we want orthogonal matrices to do the job instead of elementary row matrices. So, okay. So to explain, like in equation form, how this approach for Givens rotations and also householder is going to work is you start with A, and you're going to multiply A on the left by certain orthogonal matrices that I'll just number Q1, Q2, and I'm taking a transpose. Now, if I take an orthogonal matrix and take the transpose, that's also an orthogonal matrix. And you'll see why I'm transposing in a little bit. So you keep going and apply a whole series of these matrices. And so how many? It depends on the algorithm that you're using. I'll just say K in this case. And the final result is some upper triangular matrix R. So then that would mean that A would be equal to, if I were to multiply both sides of this equation on the left by first QK, then QK minus 1, and so forth, all the way down to Q1 and Q2, I'd have Q1, Q2, QK, R. And the product of all of these orthogonal matrices, Q1 up to QK, that is what we call Q. So it's similar to Gauss elimination in that here we had A, and we multiplied on the left by a bunch of elementary row matrices that were unit lower triangular. Then that achieves a factorization. A is equal to the product of the inverses of all of these unit lower triangular matrices, which are also unit lower triangular in that setting. And then the product of all of those would be L. And then what you're reducing to is your upper triangular matrix, R in this case, whereas it was U in Gaussian elimination. So we're going to see what sort of orthogonal matrices can we use. Each one of these very simple in structure to make progress towards reducing A to upper triangular form.
I have a question, if you don't mind me asking. So over here, I understand what you did over here to get to after the implication arrow, I guess.
Yeah.
And so, and also, you said these are orthogonal, right? They're all orthogonal? Okay. Yeah. Is this the case with, like, any one of them? Because you know how, like, when you take the, say, just inverse, right, of something, so if I take the inverse of one side, then the other, and take the inverse of the other, it kind of looks something like that, where the inverse appears. Is this something that will always work?
Okay.
Pose.
That's okay. That's each QI transpose is equal to QI inverse. That's one way of characterizing an orthogonal matrix, but transpose is the inverse. And that's why I can multiply each of these by both sides by QK, QK minus 1, etc., all the way down to Q2, Q1 to effectively move these over to the other side. Because I'm multiplying by QK, for instance, and it cancels the QK transpose. And that's why I'm left with only A at the end. So I'm using the fact that, okay, and this comes from the fact that QI transpose, QI. If you multiply these in either order, is the identity. Because this is the same thing as saying the inverse is a transpose. So that's one thing to justify. That's what justifies going from here to here.
Okay.
And to get from here to here, if Q1 and Q2 are orthogonal matrices individually, then the product Q1, Q2 also orthogonal. So because I know each one of these factors is orthogonal, I know that Q is also orthogonal. Okay. And I could draw a parallel of Gauss elimination. Being unit lower triangular, like our row operations, is preserved by multiplication and inversion. And that's why I was multiplying A by a bunch of unit lower triangular matrices to get U. And then I could move those to the other side by multiplying by the inverse, which is also unit lower triangular. And that's how I was able to conclude that A is a product of a lower triangular times an upper triangular. That when I took all those row operation matrices and moved them to the other side, I knew that what I had on the other side is still unit lower triangular. And then I multiply all of them together, and it's still unit lower triangular. So things like being orthogonal or being unit lower triangular are nice properties in the sense that they survive things like multiplication and inversion and all that.
Okay, so this is, again, very specifically to do with orthogonal. Like the transpose won't always be the inverse as far as...
Right.
Okay.
Yeah, so I could generalize this and say, oh, this is the inverse.
Mm-hmm.
Then the same statement applies to QR factorization and Gauss elimination. Only when it's orthogonal can I just move things around by taking a transpose.
Okay. Thank you.
And that's very important because the transpose is really easy to get. You don't have to compute anything at all. You're just switching rows and columns. Whereas a general matrix to invert is a huge pain. Elementary row matrices, thankfully, those were easy to invert too. You just had to change a sign, so that was nice. But we like orthogonal matrices because, actually, for two reasons. Okay. First reason, trivial to invert, because all you're doing is taking a transpose. And second, and this is something that does not apply to row operations at all, perfectly conditioned. And meaning that if Q is orthogonal, then at least in a 2 norm, well, that'd be the norm of Q times the norm of Q inverse. But that's the same as that's 2 norm. But that's the same as 2 norm of Q, 2 norm of Q transpose. And I don't have the time to show this here, but at least with a 2 norm, the norm of the matrix is the same as the norm of a transpose. It's actually 1. And that's because in the 2 norm, there's a property I showed you of orthogonal matrices earlier that we used for least squares problem. That if you take any vector x and multiply by orthogonal matrix, its 2 norm doesn't change. So that's why the norm of 2 norm of an orthogonal matrix is always 1. Therefore, its condition number is 1, and that's the smallest condition number you can have. So because they're perfectly conditioned, orthogonal matrices are nice to work with because it helps prevent accumulation of round-off error when you're transforming matrices using orthogonal matrices instead of something else. Okay.
Thank you.
Yep. All right, so if we're trying to zero out entries like in Gauss elimination that are below the diagonal to get upper triangular form, and we could do that by multiplying by an orthogonal matrix. And I say pre-multiply. What I mean by that is multiplying on the left. Then, and that's what I was mentioning up here, the accumulation of all of these will be orthogonal. So I'm going to work with a simple example, 2 by 2 matrix. So I need to make A upper triangular. And if it's 2 by 2, I only need to zero out one element. So here's my matrix A. I need to multiply it by a matrix of this form to make it upper triangular. So I just need to zero out this one entry here. Now, now I need to make sure that this matrix is actually an orthogonal matrix. So, dang it. C is equal to cosine theta. S is equal to sine theta. Right now, we don't really care so much what theta actually is, as long as we get this entry to be zeroed. But by saying C is a cosine, S is a sine, then we have C cosine squared plus sine squared equals 1. The only trig identity that we can pretty much count on most students to remember. So if I were to take this matrix and call this Q, then you can work it out that Q transpose Q actually is identity. So in fact, just about any orthogonal 2x2 matrix, it can be expressed in this form for some cosine and sine. Because you can describe orthogonal matrices as rotations. This implements a rotation in two-dimensional space, and that's actually where the term Given's rotation gets its name. So if I carry out this matrix multiplication and I set the 2-1 entry of a result equal to 0, so that's what I'm looking for. Oh. Okay. That would give me this. So I need C and S to satisfy this for whatever entries A11 and A21 I'm given. So what I can do is, okay, I took this term, the minus SA11, moved it to the other side, then squared both sides, and that got me this. But sine squared is 1 minus cosine squared. So I substitute that here. So now I have this equal to this, which lets me solve for C squared. And if I go ahead and do that, then this is what I get, plus or minus. I could choose either one. I'll just go ahead and, by convention, choose the plus sign. So now I can solve for S squared in terms of C squared. And I get this. Again, I have a choice of plus or minus. I'll go ahead and choose plus. Okay. So this choice of C and S, when used in this matrix, will ensure that this entry is 0. Now, what about this entry? I go ahead and compute that by filling in C and S, and I simplify everything, and this is what I get. Now, it makes sense that R11 turns out to be the magnitude of this column, which is the square root of sum of squares. Why? Because I'm taking this column and multiplying it by an orthogonal matrix, which will preserve the Euclidean length. So all of the length ends up being put in here, this element, because the other element is being zeroed. So now I have a way of choosing C and S to reduce A to upper triangular form. And that's by choosing C and S this way, and choosing a plus sign. So to summarize, so this matrix that I've obtained, so cosine minus sine, sine cosine, that's a Givens rotation. So that's where the term comes from. Because and the reason why it's called a Givens rotation because it actually performs a rotation. It takes whatever point you multiply, like if you multiply this by any two-dimensional vector, it will rotate it through the angle theta. Now, if you multiply by q, it will rotate clockwise. If you multiply by q transpose, which is the inverse, it'll rotate counterclockwise. Wait. Did I just have it backwards? I think I have it backwards. Okay. Hold on. Yeah, I had it backwards, sorry. Q transpose rotates clockwise. Multiplying by Q is counterclockwise. Okay. All right. So if I have some point A, B in two-dimensional space, and I multiply it by Q transpose, then it brings that point to the positive x-axis. So it's a point x is r and y is 0. So whatever rotation brought it to A, B in the first place, this has the effect of undoing that rotation to bring it back to the positive x-axis. And in a way that preserves length, because the length of this column is square root of a squared plus b squared. The length of this is also square root of a squared plus b squared. All right, so questions about what a Givens rotation is. So one Givens rotation like this can be used to zero one entry, the second entry of a two vector. So we want to use a bunch of these to work on a whole matrix of whatever size and reduce it to upper triangular form. So how do we do that? All right, so let's suppose I have some vector that I want to work with. So here's my vector, and I don't really care what's in this vector except at two particular positions where we have this A and B. So I want to use A to zero out B. And the other entries that are marked by X's, I don't care about them. I'm not going to touch them. So the way you do that, using a Givens rotation, is the following. I form a matrix. Now blank space is interpreted as 0. Notice I have mostly ones down the diagonal, so it's identity for most of a matrix, except in the same rows where we have A and B, those rows and columns, I put my cosine and sine, so CS minus SC. So this is my Q transpose from before that I'm putting here. Now, when I multiply this vector by this matrix, all the entries where you see x's will not change. Only these two positions will change. So A and B gets changed to R and 0. So I've used this entry to zero out this one. Basically what I'm doing is I'm rotating these, the vector consisting of A and B to a positive x-axis to get rid of this entry right here. So that's how I can take any two rows and rotate them by multiplying by this kind of matrix on the left. And it'll rotate those rows in such a way as to zero out this entry. So I can apply this to a vector of any length. So now I'm going to use a bunch of rotations of this form to reduce A to upper triangular form. Now, if A is m by n, then I have to work on m columns. No, that's totally wrong. N columns. And within each column, I have to zero out first m minus 1 entries, then m minus 2, like all the entries below the diagonal. So that's in the order of m times n entries. Now, every time I perform a rotation, if I'm taking A and multiplying it by an orthogonal matrix like this one, a Gibbons rotation, I'm going to take two rows and rotate them. Each row has n elements because there are n columns. So each individual rotation takes this many arithmetic floating point arithmetic operations. So to get the total amount of work involved, I have to multiply this amount of work per rotation times the number of rotations, and that's the overall complexity, m times n squared. So that's how expensive it is to compute a QR factorization. Any questions so far? Now, soon I'll do an example of how this is carried out, but first I need to make a point about floating point arithmetic and how that can complicate matters. Now, here's the formulas I gave for C and S. Now, one difficulty here is that if we compute these entries as exactly as written, that could be a problem, like this entry right here, because let's suppose either A or B is extremely large, like close to the largest number you can represent. But then you square it. So now it's way too large. If it's too large to be represented, then like A squared or B squared would be represented as infinity in the floating point number system. So the operation will fail. So what we need to do is, and this is actually a homework problem that I give in Math 460, 560, it's in chapter 2 on how to fix this. So I'm going to use that here to show how we can rewrite these into equivalent formulas that are that don't have this risk. So there's two cases. If you assume that B is the larger, then we let T equal A over B. So this is guaranteed to be less than or equal to 1 in absolute value. So now this operation is no problem because we're just working with nice, reasonably sized numbers. SGN of B, that's the sign of B. So 1 if B is positive and minus 1 if B is negative. So we compute S this way, your sine, and then you compute your cosine this way. So that's a workaround for this floating point arithmetic issue. And then if A is the larger, it's the same idea. You just reverse the roles of everything. Or just flip A and B around. Yeah. And here we compute the cosine in this way and then sine this way. I should mention that in the book, I actually have 1 in the numerator. That's wrong. It needs to be the sine of b in this case, the sine of a in this case. And those other formulas in the book, they will work, but they're not actually equivalent to these. They might be negative. So any practical implementation for a given rotation should use these. Okay. So now I want to illustrate how we can use Gibbons rotations to compute a QR factorization. So here I have a 5 by 3 matrix. So I want to reduce this to a matrix R that's 5 by 3 and is upper triangular. So I have to zero out these 4 entries in the first column, the last 3 entries in the second column, last 2 entries in the third column. So I have 9 entries in total to wipe out. And I'll do them one at a time. So what you do is you go from left to right, just like in Gauss elimination, first column, second column, third column. But one thing is different from Gauss elimination. Gauss elimination, once you got to your column, you would go from the diagonal down. Here, we're going to start from the bottom up and zeroing entries. So this one right here, oops, dang it. This entry right here in the 5-1 position is going to be the first to go. And I'm going to use the entry right above it, this one, to help me do it. So here's my Gibbons rotation. I take out the 2 entries I want to work with, 4-1 and 5-1. The second entry is the one I want to get rid of. And the other entry is one right above it. That's why I'm going from the bottom up. So if I focus just on these 2, this is my Gibbons rotation, my cosine sine pair, using these formulas for the case where this is A, it's playing a role of A, this is playing a role of B. And B is the one that gets zeroed. So I figure out my cosine sine pair, and that's what will wipe out this entry into 5-1 position. So once I figure that out, I have to apply this same rotation to these 2 entries and these 2 and these 2, because you're rotating the entire rows. So these entries will change according to this. These entries will be changed too, which will affect upcoming operations. So when I apply this rotation, okay. So here is my full Gibbons rotation. You see its identity, except for in rows 4 and 5, where I have my rotation, and it's applied to this original matrix A. Because of these 3 rows being corresponding to identity, the first 3 rows will not be touched. You'll see they don't change at all. Rows 4 and 5, basically I'm taking a linear combination of these rows, this linear combination here, and that gives me row 4. Then I'm taking this linear combination of rows 4 and 5, and that will give you row 5. And where we see that this entry is zeroed. The other entries are affected just because I can't just apply this row rotation only to these entries. I'm multiplying on the left. That performs operations on entire rows. So here's my first step towards upper triangularity, zeroing out this entry. Now I move up the first column. I'm going to work with this entry and this one. This one is the one to be zeroed. So I'm going to work on entries 3-1 and 4-1. So I do the same thing. I look at these two entries, figure out the right cosine sine pair that will cause this one to be zeroed. And then I apply that to rows 3 and 4. So I just keep moving up. So what does that look like? Here's my Givens rotation. Notice its identity in rows 1, 2, and 5. Rows 3 and 4 are where I have this cosine sine pair arranged as a Givens rotation. And I work on rows 3 and 4. And now that entry is zeroed. These other entries are changed. And that's how this process will continue to unfold. I'll keep going up the first column to zero this entry, then this entry. Then I'll be done. And I can move to the second column. Again, start from the bottom to get rid of this, this, and then the third column to wipe out this entry and this one. So any questions about how this process is unfolding? As I reveal more of this. All right. So here I'm working on rows 2 and 3. So we're wiping that out. And then finishing the first column. All right, so now I work on rows 1 and 2, so the rest of its Givens rotation is identity. Now, we don't actually form this whole matrix, because that would be a waste. We figure out our cosine sine pair, and then we would use that to rotate the 2 rows in question. And once these 2 are rotated, the first column is finished. These columns have all been changed, but now I will move to the second column and work on this one, that entry. So you can see I work on these 2 to zero out the one in row 5, column 2. Okay. All right, so I'll introduce the rest of this. It's pretty lengthy. All right, so after working on rows 4 and 5, then rows 3 and 4 to wipe out this entry. So we're making making progress down up the second column, and then one more entry. Whoops. To finish off the second column. Okay. So these 2 rows are what we stop with. So now the first 2 columns are complete. When we just go back to the bottom and have to eliminate just 2 entries of a third column, and then we'll be done. Okay, so back down to the bottom to get rid of that one. And then finally, just about done. So you can look at this later and see all the rotations that were used and what effect they had on the matrix. Okay. So then Okay, so then we get to upper triangular form after eliminating all the entries below the diagonal. That is our matrix R. Okay. Okay, something seems odd here in what I've written. Whoops. Okay. So if I take all of those Givens rotations and multiply them together, if it's H1, H2, H3, that's actually for household. I'm not sure what this is doing here. So yay, never a mistake in the book. That I'll have to deal with at some point. Okay. All right. Okay. So I use a total of 1, 2, 3, 4, 9 Givens rotations. If I multiply them all together, then from left to right, then so actually I'm going to fix this. If I name the Givens rotations after the entries they were used to 0, so like first I did the 5-1 entry, and 4-1, 3-1, 2-1, and then moving to the second column. So 5-2, 4-2, 3-2, and then 5-3, 4-3. So multiplying them together in this order, we give you a matrix Q so that A is equal to Q times R, where R is this upper triangular matrix. So what I need to do now is describe the overall algorithm. Okay. Okay, something is. If I write a function in Matlab, for instance, givens AB, where B is the entry you want to 0, and A is the entry that you're using to help 0 it, and CS is a cosine sine pair that'll get the job done. So in other words, it would implement these equations here, equations 1 and 2. So if I write a MATLAB function that will check whether B is greater or equal to A or vice versa, and just compute these and return them as output, the cosine and sine. So that'd be like a helper function. So if I assume that I have such a function available, or I go ahead and write it myself, then I'm going to use this notation, GIJCS, which is meant to specify which rows are being rotated, row I and row J, using that cosine sine pair, and that'll have the effect of zeroing out the value B. So if so V is a vector like a column of A that has these entries in the I and J positions, then I carry out this Givens rotation, multiply it by its transpose, then it will zero out the entry in position J. So that's how one rotation is handled. Okay. So here's the algorithm. Okay. QR factorization using Givens rotations. So it's formalizing what I showed you in the example. So first, Q is the identity matrix. R will just be A. So I'm going to keep working on R to make it upper triangular. And then as I do, I can accumulate Givens rotations of a product of them, and that will give me Q. So I go through all the columns from left to right. In each column, I start at the bottom, that's row M, and I work my way up. So I'm counting backwards to eliminate all entries starting from row M all the way up to row J plus 1, so everything that's below the diagonal. Now, Rij is the entry of 1 to 0. Here's the entry right above it. I use those two entries to give me my cosine sine pair for my rotation. Once I have that rotation, this matrix is a matrix I was showing you in the example that's mostly identity, and then we have these this 2x2 rotation matrix. So multiplying on the left by the transpose will zero out this entry. Then I take that same rotation and multiply it on the right of Q. So that's how I accumulate all the products of all the given rotations. So once I'm finished with all this, R will be reduced to upper triangular form, Q will be the product of all the given rotations, and so then I'll have my both my factors. A is Q times R. Now, a few comments I need to make about the algorithm. Here, because I'm multiplying Q on the right by Givens rotation, this is actually rotating columns. So Givens rotation rotates rows with multiplying on the left, columns with multiplying on the right. Now, in an efficient implementation, you would not form all of G, because that's mostly identity. All you do is use C and S to take a right linear combinations of row I minus 1 and row I of R. So you're going to overwrite rows I minus 1 and I with their rotated versions. And the other rows will be left alone. Here, too, you're performing columns, so it's only going to affect columns I minus 1 and I. So you're just going to work on those. Okay. Also, when you're performing this rotation, you're working on column J. Well, these rows in first columns up through J minus 1 are already 0. So you're not going to work on those portions of those rows either. So each rotation as you go from left to right for your columns is going to end up doing less and less work, just because there's fewer non-zero entries in those rows to do anything with. Okay. All right. Last comments about Givens QR, and then I'll be able to take some time to talk about homework. Okay. This is the actual number of rotations that are needed. I said order m times n. It's somewhat less than that. Now, one thing that's interesting about Givens rotations to use to compute the QR factorization is each rotation, as I mentioned, only affects 2 rows of A. Now, in how I've shown the algorithm, we start from the bottom and work our way up. But you don't have to do it that way, because so what you could do is you could change the order of rotations to work on different rows. And So then you can apply them in parallel. So if you have parallel architecture, you can work in the rows differently in order to save yourself some time. Yeah. So like, for example, if I have a matrix of 10 rows, I can rotate rows 10 and 9, and then in parallel, 8 and 7, and then also in parallel, 6 and 5. And then continue from there to, so that'll eliminate certain entries all at one sweep. And then I can use different row rotations to get the rest of them. So I've only shown you one possible ordering. There are different ones that are possible. So now I'm showing you 3 different methods to compute QR. Gibbons rotations tend to be preferable for this reason that they can be parallelized. Another good reason for them is suppose you change A, like you add a row to A or you delete a column of A. You don't want to have to recompute the QR factorization from scratch, and you don't have to. It actually is possible to update QR factorizations with less work, and it's Gibbons rotations that are best for doing that. So also a more efficient way is a sparse matrix. So this is because each one rotation is very pinpoint. It goes after one entry of a matrix. So that gives an advantage. It's more flexible. So these are key reasons why we like Gibbons rotations compared to the other methods. But they have their pluses too. So any questions about Gibbons QR before I talk about homework? Yeah, I kind of figured out one way to talk about homework. Okay. All right. Now, one problem that is certainly a bear is 3.2.20. Solve AXB. Now, solve AXB by itself does very little. It delegates most of the work. Use your Gauss-Elim function from problem 3.2.11. I should mention that here. Except modified for partial pivoting, which is what I'll talk about in a little bit. But it's that version as opposed to the other one that was earlier. Forward substitution, that's one of the other problems. And then back sub. I did not assign this, but once you've done forward substitution, this one is really quick to do because in both cases you're translating pretty directly an algorithm that's been given. So this is the algorithm in this case for back substitution. So solve AXB would call your Gauss-Elim function to get the matrix that's being called LU that has both U and the interesting part of L in it. Then that matrix gets passed through forward substitution, where it'll access a lower triangular part, and then also pass it to back sub, so that where the upper triangular part will be accessed for back substitution. That's it. And solve AXB by itself is literally just a few lines long. You could do it in 4 lines, honestly. The main part of the work will be here. That this function from this problem will already do Gauss elimination, but now you got to modify it for partial pivoting, and that's where the main difficulty. Okay. So now I'll give some pointers about that. Okay. Whoops. Now, you're working in column J in Gauss elimination, and you need to check a part of that column from the diagonal to the bottom. That's how you describe it in Matlab. Rows J through N, column J. So that's the portion of a column that you need to check. So the way you do that is use MATLAB's max function. So if you tell MATLAB to use max to find a maximum value of a vector, you can actually have it return two outputs, and that's what you want in this case. V is the actual max, the value. I is the position where it found it. You want to know not just what is the largest element to put it in diagonal, but you also need to know where it was found, because that tells you what row you want to swap with row J. Now here's something to be very careful about, though. Okay. Dang it. Stop it. Okay. Now, let's suppose you take this portion of column J, you pass it to max. Don't forget absolute value. And it tells you, okay, here's largest element, and here's where it was found. This value that's returned is not the index of a row to swap, because you did not pass the whole column, you only passed part of a column. You have to correct this value to get the actual row where the largest element was found. Okay. So to give an example, okay. Suppose you're in the third column, and you go ahead and take the max of absolute value of this, and it tells you that the fourth entry is the largest. So in other words, the value of the return value I is 4. So the fourth element of this is the largest. That means the sixth row is the one you want to swap with. So you're going to swap rows 3 and 6 because you have to account for the fact that only part of a column was passed, because the first two entries were excluded because they're above a diagonal. So just make sure to correct the output returned by max so that you know which rows to swap. And again, you want absolute value. ABS, the MATLAB function ABS, will take the absolute value of its input argument. Now, once you know what rows to swap, how do you swap? MATLAB's indexing features make that easy to do. It goes like this. So here, on the right side, you're extracting rows P and row P and row J in that order. And then comma colon means take all columns. Then they're assigned to rows J and P in that order. This performs a row swap. And it swaps the entire row because you're taking all the columns, which is what you want for Gauss elimination. Okay. Now, aside from doing the actual row swaps, for Gauss elimination and pivoting, you need to keep track of the row interchanges, because once you're finished with Gauss elimination, you have to solve this system, Ly equals PB, where P is a row interchange, matrix of row interchanges that's now applied to B. Now, you're not going to construct a permutation matrix because that's wasteful. Fortunately, there's an efficient and relatively easy way to handle this. You make a vector of indices, 1 to n. So that's how you do it using a colon operator. So that will implicitly represent your matrix P. So as you swap rows doing this, you're swapping rows J and P. Also swap entries of capital P. That way, you're indicating here are the indices of rows that I swapped. So this has to be returned as output from Gauss elim because so this would be the final ordering of the rows after all row swaps are taken into account. And then for forward substitution, Matlab makes it really easy to apply this scrambling of rows to B. You just do this. Because P is a vector of indices in some order. So this says take the elements of B in that order. And since P represents how the indices of the original rows were scrambled because of row interchanges, B will have the same row interchanges applied. Those same row interchanges applied to it. So this vector, not the original B, this vector is what you use in forward substitution. I know there's a lot here. That's an understatement. Are there questions about what's going on here with partial pivoting? Wow, what a quiet bunch we have. All right. I have a little time. I want to say something about 338. This is about symmetric positive definite matrices. Asymmetric positive definite. So is A inverse. So if you use properties of symmetric positive definite or SPD matrices, that can tell you why A is at least invertible. And that's, in fact, that's discussed there among the properties because okay. Oh, sorry, I just muted my speakers there. All right, so focusing on the determinant is helpful for that. The interesting part of the problem is, given that A is at least has an inverse, so in other words, it at least exists. And it's actually one of the properties of a transpose that if A is symmetric and invertible, its inverse is symmetric. So there's really nothing to do there about symmetry either, but just show it as positive definite. You just show that X transpose A inverse X is positive whenever X is a non-zero vector. Based on the same being true of A. If A is invertible, then for any non-zero vector X, there exists a unique vector Y such that AY is equal to X. Or equivalently, Y is equal to A inverse X. So use this to try to find a relationship between X transpose A inverse X being positive versus X transpose AX. Now, the vector in question can be any non-zero vector as long as it's the same vector on both sides. All right, so see what you can do with that by virtue of A being invertible, because you have to be able to, it takes using a property of invertible matrices to show this. And this is a property that's best to use, that if A is invertible, then this system can always be solved. That any vector that you have, any non-zero vector X can be written as any non-zero vector X, you have this relationship. Any questions about that? This problem I have talked about before. Trying to prove by contradiction. That the hint I gave before was that this matrix, if it's singular, then this system has a non-trivial solution. Okay. That you want to use a submultiplicative property. So for generic A and X, matrix vector product A times X is less than or equal to norm of A times the norm of X. All right. I'm just about out of time. Fortunately, with 610, there's only 4 or 5 assignments all semester long, aside from the quizzes. So there's a good amount of time in between homework suggested due dates. So I know I'd set today as the due date for this one, but I'd be definitely fine if you take a little more time, since I'm just talking about these today. Plus, there's no way I would start grading them until the end of a week anyway. Probably on Saturday. So any last questions? Or I should say any questions at all, because you've been a very quiet bunch.
I have a question.
Yep.
4110.
Wait, which one?
4110 expression 4110.
Oh, okay. Okay.
So if you can explain that the last part of the problem.
Oh.
If not, how could it be fixed so that they are?
Okay. All right. So this gets to the next assignment. Okay. So what you can do is, so if A is equal to R1 transpose R1 as negative diagonal entries. Okay. Whoops. All right. And the problem asked about is how to fix them so that they are positive. So I'm gonna try to be careful not to give away too much, but okay. All right. So the proper Cholesky factorization of A would be A equals tilde R1 transpose tilde R1, where tilde R1 has positive diagonal entries. What is an easy way to obtain tilde R1 from the R1 that you have? So, like, suppose you had some other algorithm for Cholesky that didn't really give a true Cholesky, but it gave you R1 that satisfied this, but has negative diagonal entries. And that's why the Cholesky factorization is unique, but only if you require positive diagonal entries. If you don't require that, there's actually infinitely many factorizations of this form possible where R1 is upper triangular. And the thing is, there's all different kind of ways of transforming matrices, like, you know, multiplying them by something, etc., in such a way that this, like here we have this equation that you're given, and you want this to still be the case. So, yeah, you want to do something to R1 that would preserve this equation. And what would that be? So they're talking about. What?
Can't we just change the sign of the diagonal entries? Because so when I tried this, I tried creating an upper triangular matrix like this, and then change the sign. So I used one where we have negative diagonal entries and one where we had positive diagonal entries. And when I multiplied the matrix, it was kind of different.
Yeah, if the goal of this problem is to show why, if you want to do something like that, and if it works, show why it works.
I still don't get how to like. So the matrix was still symmetric, positive, definite.
Yeah.
So the symmetry was different. So let's say I have -9 on the 2, 3, 3, 2, and 3. So something like -15, -15, and I couldn't really figure out what to do to multiply that would give us the same elements. So I was really confused.
Okay, yeah, because simply changing the sign of the entries, the diagonal entries, that alone would not do it. But that is somewhat on the right track. But that alone is not enough. Because what you could do is, okay, I'll give one more hint. So if you have your original factorization, and I'm sticking an identity in here. Now, you could write identity as whatever you want, like as long as it's something that's equal identity, like a matrix times its inverse or something of that nature, or a matrix times its transpose if it's orthogonal, as a starting point to figure out what should go in here that like you can break this up into a couple factors that could be applied to R1 and also to R1 transpose. That would have the effect of changing R1 in the right way to give it positive diagonal entries and still have its product equal to A.
Okay, so I see. So that identity matrix now can be two different matrices that won't multiply give us identity, right?
Yes. That way you ensure that the product is still A.
Okay.
Yeah.
Okay.
So I would say that while simply changing the diagonal entries is not enough, that is a step in the right direction. So this is for everyone else's benefit too. Think about trying to take that a step further.
Okay.
Okay. Well, I should stop this now just because I have my next class in 9 minutes, which some of you are in. So good luck. I'll stop recording at this point.